So what did we learn in the last lecture? Let's have a review. We talked about the Schroedinger equation. This is the general Schroedinger equation. Again, what you said is for any state phi, its rate of change of the state is proportional to the Hamiltonian times the state. And that is like the F equal to ma in quantum mechanics. In one qubit system, this is very simple. Because this phi, or sometimes I call it psi, is in this case, right, equals to alpha beta. If the basis state is 0 and 1, this is just alpha 0 plus beta 1. For one qubit, it is a two-dimensional system, although it has complex coefficient, C2 space, right? But you only just two-dimensional. You have alpha and beta to describe a state. How does alpha and beta change? It is given by this equation. The rate of change of alpha, partial t, equals to h00 times alpha plus h01 times beta. This is the 2x2 matrix. So we are going to solve the one qubit system by using this equation. Then we also talk about the spin. We first try to understand some basics of the spin, including we take it for granted that for electron, it can have a spin half, plus or minus. Each of the spins will give you a corresponding angular momentum, just like the real spin, the real space spins we have in classical case. And the angular momentum is just plus minus h bar over half. And we know that from classical physics, anything that has the angular momentum and with charge, you're going to get magnetic moment. So for electron, in general, the spin, the magnetic moment related to the spin is called the spin magnetic moment. It is given by this equation. Now, last time I did not really emphasize much, but this time I introduced something called gamma, which is the gyromagnetic ratio. You see that the magnetic moment is just equal to the gamma times the spin angular momentum. So you see that gyromagnetic ratio basically just tell you what is the ratio between the magnetic moment and the angular momentum. Okay. Now we have this G, which is called the G factor. For electron, the G factor is very close to -2. -2.00 something. Okay. So that's why sometimes I can just cancel this G with this 2 to get the gyromagnetic ratio almost equal to E over N. If your G is 2, then you get E over N. Okay. Now, we also have something called Bohr magneton. It's approximately equal to the magnetic moment of the electron. And it is EH bar divided by 2M. Right? So if we assume G is approximately equal to 2, then the magnetic moment is just equal to the Bohr magneton. This is not very important in this class. So if you feel confusing, you don't need to dig too deep, right? The main point is that you understand electron has a spin half. Its magnetic moment is h bar divided by 2. Its angular momentum is h bar divided by 2. Then its corresponding magnetic moment is about E divided by M times h bar divided by 2. Okay, you can use this equation. Now, when you have magnetic moment and you put it in the external magnetic field, you will create an interaction because the magnetic field and the magnetic moment are going to have interaction, and then it will change the energy of the system. It is given by this equation, negative mu dot B, which is a dot product. And if you don't see this, we can just spell it out. It's the magnitude of the magnetic moment times the magnetic field times the angle between them. So if they align in the same direction, you have a lower energy. But if they align in opposite direction, you have higher energy. But you need to remember, this is talking about the magnetic moment and the magnetic field. For spin, because G is negative for electron, then it means the opposite thing. If the spin, for example, in this case, magnetic moment, the external magnetic field is pointing up. If your spin is pointing down, it means your magnetic moment is pointing up. So you have a lower energy, right? The energy, there's a splitting of the energy from before having magnetic field, and up to you have magnetic field pointing up, you reduce the energy. On the other hand, if the spin is also pointing up, it means the magnetic moment is pointing down. Again, because G is negative, right? G is negative too. So as a result, your system has a higher energy. Okay, so this is a very important thing that I would like you to memorize, and be careful, because sometimes people may talking about the spin of a positive charge, then the story will be different depending on the G. For example, proton it has a positive value. Okay. So with this, then we try to construct the Hamiltonian of this system when I have an external magnetic field pointing up. So I put an electron spin under an external magnetic field. What is the Hamiltonian? When it is pointing up, this is a simplified case. The Hamiltonian is just equal to the Pauli matrix times this magnetic moment times the magnetic field's magnitude. And we solve the equation. We solve the Schroedinger equation, and we found that the state of the electron will change by precessing about this z-axis. If this one looks complicated to you, then you just recall what we have talking about is psi equals to alpha 0 plus beta. This is just a general state, right? Now, as the time goes by, of course, this can be alpha and beta will be time dependent because we put it under the external magnetic field. But we also know that we already proved earlier that despite these two are two complex numbers, but we don't care about global phase, and also because their normalization needs to be 1, we can represent this as cosine theta divided by 2 e to the power negative I phi divided by 2 0 plus sine theta divided by 2 e to the power I phi divided by 2 1. So that this is represented on the broad sphere. So every state you have alpha and beta, but on the broad sphere, it represents that it has this polar angle of theta and azimuthal angle of phi on this broad sphere, right? So after we solve this equation, we get something similar. The theta part doesn't change, cosine theta divided by 2, sine theta divided by 2. The phi part is changed, but how it is changed? The form is still the same, negative I divided by 2 times something. I divided by 2 times something. And this something is the original phi, the initial angle, plus something. So basically, it's that when the time is 0, you were in the original state. When the time increases, this phi will keep changing, right? But theta does not change. And that's why this is called a precession. You just rotate along the latitude, right? Like the globe, right? Even I've messed up latitude or longitude, but just rotating in this direction. Okay, and we got this by very rigorous proof in our previous lecture. Now, it is rotating linearly with the time. So then it means there's a frequency, right? Because this is t. So d, this theta dt, is going to give me something called the Larmor precession frequency. You can see if I have a larger magnetic field, I will rotate faster. Now, if I just achieve g as 2, the g factor, like we discussed earlier, then the Larmor precession frequency is just b e divided by m. Okay, and you look from top, is rotating anti-clockwise. Okay, And then at the end of the last lecture, we talked about the spin angular momentum operator. We need this tool in order to do more advanced treatment. Okay. Remember, we just talked about the angular momentum as here. Spin angular momentum is just a scalar, right? We just say it has plus minus h bar. But in which direction it is? So we have an operator at our disposal, right? So S equal to h bar times the Pauli matrix is the spin angular momentum operator. Now, first of all, we want to understand what is the meaning of this one? Well, this is just Pauli vector, so it is sigma x hat plus sigma y hat plus sigma z hat. So this is a vector. Okay, its x component is a matrix. Okay, so if I spell it out, you will get this. And then what I try to show you is that if this is to check if this is correct. For example, if say this is angular momentum operator, you expect if you sandwich a state to it, you should get the correct angular momentum, right? So I check, for example, if it is zero state, it means that the spin is pointing up. I do expect it has a angular momentum of h bar divided by 2z, right? The magnitude is h bar divided by 2, right? Angular momentum, right? H bar divided by 2. The magnitude is h bar divided by 2. But what is the direction? It is z, right? So, and I showed you last time, right? We can do more in the homework to try different things. But here, we don't go too deep. But basically, it just take it for granted. The spin angular momentum operator is this. And we can construct this operator like how we construct the Hamiltonian before using for this case, like we did it before. Use the eigenvalue and also with all the eigenvalue and also and the eigenstate. Okay. So good.